Hello, today we are going to look at volcanoes and earthquakes. Please be sure to take notes in your notebook on the pages indicated in your Google assignment. So first we're going to start with volcanoes. In essence, what is a volcano? Well, quite simply put, volcanoes are simply the activity of the molten material that is under the Earth's crust being expressed above ground. Volcanoes are named after the Roman god Vulcan, who was the blacksmith of the gods, and so that harkens back to that whole molten material working with super hot materials. There are three types of volcanoes based on eruption history. There are first the active volcanoes, and there are 550 known active volcanoes, give or take, across the world, and several could be erupting at any given time. There's also what we refer to as dormant volcanoes, and dormant volcanoes have not erupted in historical time, but are capable of still erupting. And finally, we have extinct volcanoes, which have also not erupted in historical time, but they have no signs of any activity, so that we would say they are no longer able to erupt. Volcanoes have several products, but basically we can narrow it down to three types. There's lava, there's igneous rocks, and then the debris and the pyroclastics. Lava is the molten rock material that has reached the surface. So basically, when it's underground, it's magma. When it comes to the surface, it becomes lava. There are several different types of lava, and depending on how sticky the lava was, how thick it was, how hot it was, how it erupts, it makes different types of lavas and lava surfaces. One of the main products of volcanoes are what we call the volatiles, and so it could be dissolved gaseous materials. And those dissolved gaseous materials in the magma are what produce the explosive volcanic activity when that magma hits the surface and all that pressure is released. Typical volcanic gases are going to be things like water, carbon dioxide, nitrogen, sulfur oxides, carbon monoxide, hydrogen chloride, and halogen gases like fluorine and chlorine. Basically, what it comes down to is many of those dissolved gaseous materials are deadly when breathed in. There's also pyroclastics, and pyroclastics are probably one of the more dangerous products of a volcano. Pyroclastic flow is where you have hot material that's deadly to be breathed in, moving extremely fast from a volcano. In fact, when we found people in Pompeii after Vesuvius blew up, those people were preserved and frozen perfectly in time because the pyroclastics came through so fast and so completely and basically just instantly stopped life in that moment. The pyroclastic material then is going to be divided and described based on the fragment size, where we have volcanic ash, which is the smallest particles, very fine, travels great distances, all the way up to what we refer to as bombs, which are very large chunks of rock and solidified magma that fall to the earth. Here are some pictures of the different types of material deposits that you can get with volcanic eruptions. We have many different types of volcanoes. They're not all those nice cone-shaped mountains like we think of volcanoes. So the first type of volcano that we have is what we refer to as a shield volcano. It's going to be most often found in oceanic areas, and it has very little pyroclastic material, tends to produce fluid lavas so that they're very high temperature, low silica, and it has that broad, low profile and tends to have flank eruptions. In other words, little offshoots on its sides. The second type of volcano that we can have is the composite volcano. And the composite volcano is more what you think of when you think of the word volcano. It's called composite because the steep sides of the cone-shaped mountain are actually made up of lots of different types of material. Ash from previous eruptions, dirt, rock, different things like that. Next, we have the cinder cones. And cinder cones can exist separately as a volcano in and of themselves, or they can be stuck on the flanks of a larger volcano, like a shield volcano. They're pyroclastic mounds with very steep slopes but low heights, and they tend to be very symmetrical around their vent. Next, we have lava domes. And lava domes are kind of a bulbous surface structure that's formed when a viscous or really sticky mass of magma is extruded or pushed to the surface. These domes that are created grow slowly in size. They tend to be steep-sided, and they're often associated with extremely explosive eruptions. Next, we have the Fissure Volcano. And fissure volcanoes represent fractures or cracks through which magma erupts in areas where the tectonic plates are pulling apart. Fissure eruptions typically occur on the flanks of shield volcanoes, and they're going to be characterized by large volumes of lava flowing from that structure. We have vent volcanoes, and they can come in many shapes and sizes, but basically it's a huge opening or depression from which all of that volcanic material passes. An interesting type of volcano is the crater volcano. And in this picture, you are looking at Crater Lake on the west coast. And what happens with a crater volcano is at one point it was either a shield or a composite or a cone of some sort. The eruption was so large, it blew basically the top off the volcano and it left a crater. And Crater Lake is a dormant volcano. It still has all of the necessary things to erupt, but it doesn't or hasn't erupted in historical record. Next we have, and finally we have the caldera, which basically is a very large magma chamber that's underground with a slight depression. It could have been caused from a large explosion in the past, or it simply formed that way. Caldera volcanoes are tricky because a lot of times you don't even know that you're on top of a caldera volcano because there's no indication above ground. Yellowstone National Park actually has a caldera volcano in there. When we look at the distribution of the volcanoes along the different plates, you're going to see that the location of volcanoes goes right along with high frequency areas for earthquakes. And when we plot those out on a map, you start to see the edges of the tectonic plates. It is important, though, to remember that there are indirect effects of volcanoes. We get land building, earthquakes, mud flows, climate changes, tsunamis, gas clouds, all of these different things. But just because earthquakes and volcanoes happen in similar areas and can happen together, they are independent events and don't necessarily occur all the time together. As a recap, here are the different types of volcanoes. Take a moment, be sure that you've got these jotted down in your notes. Next, we're going to look at earthquakes. Earthquakes are caused by the sudden release of energy along faults. Okay, so that energy builds and builds and builds and builds because of those plates interacting with each other, either rubbing past, pulling apart, or crashing into each other. And when that energy gets to the point that it has to be released, that is what we refer to as an earthquake. Remember that seismic and volcanic activity occur in similar places, but they are independent events. And so the reason that they occur in similar places is because both of those occurrences depend on those plate interactions. When we talk about the theory of earthquakes, what you have is what we refer to as the rebound theory. And so in this diagram here, it's showing you if there were a fence pulled across the two plates, so the fence straddles the boundary, and those plates were slipping past each other in a transformed boundary, the first thing is going to be the deformation or the deforming of the landmass as that energy builds up. Eventually, it's going to get to the point where that energy has to release, so an earthquake occurs, and then the rocks and everything rebound to their original shape, and the whole process starts over again. Interestingly enough, there was a case in California where this very thing happened, where there was a fence that happened to be right along the fault, and after an earthquake, we ended up with the fence in those offset positions. Seismology then is the study of earthquakes, and it uses seismoscopes, but more accurately and more commonly now are seismic graphs. When we're talking about earthquakes, we're talking about the focus and the epicenter most often. The focus, or the hypocenter, is the point within the Earth that the energy is released. So again, the hypocenter, or the focus, is the point within the Earth's crust where the energy is actually released. The epicenter is what you hear about in the news, and that's actually the point on the Earth's surface directly above the focus, where we give it a location here on Earth. So if we're looking at the difference here in this diagram, you can see the focus is underneath, it radiates out the energy, and right above it is the epicenter. So because we don't have maps and roads and streets and things for inside the crust, when we refer to earthquakes, the location of earthquakes, we refer to as the epicenter, or that point directly above where we can give a location to the earthquake. So about 95% of all earthquakes happen in seismic belts, which happen to be along the plate boundaries. They tend to always occur at convergent and transform boundaries, although you do get some earthquakes associated with divergent. And again, here's a map. The dots representing the places of high frequency earthquakes. And again, you can see, just like we saw with volcanoes, those are along the plate boundaries. When we're talking about seismic waves, we're talking about body waves and surface waves. The body waves are what we use to locate the epicenter, and we have the primary waves, which get there first, and they're the fastest traveling. And we have the secondary waves, which of course get there secondarily, and they tend to be slower traveling. The S waves are going to be the ones that cause the most damage. Ironically enough, we can use earthquakes and that seismic activity to actually understand what's going on within the crust or the surface of the Earth. And so we use those seismic waves kind of like a giant sonogram for the Earth, where we understand that as the wave goes through, if we time how long it takes the wave to come back to us, we can make assertions about what material is made up of below the crust. So the waves are going to travel most quickly through bedrock, which is well-pacted, solid material. And as we go to looser materials into liquids, you will see that water, the seismic wave slows down significantly. When we locate an earthquake, we need time-distance graphs and we need travel times. And so if we're looking at that, we see from when the P wave first arrives to when the S wave arrives, that's our interval of time. We plot that interval of time onto a time distance graph. And so using that point of intersection, we know exactly how far away that particular seismograph was from the epicenter. You have to have at least 3 seismographs to find an epicenter, and we use a process called triangulation, where you plot the distance of the 3 places, and where the 3 lines meet is where the epicenter of the earthquake is. We measure earthquakes on 2 different scales. We can either measure the intensity of the earthquake or the magnitude of the earthquake. For intensity, we use the Mercalli scale. Intensity is kind of a qualitative measure where basically you look at different rubrics to assess the amount of destruction done, and that tells you how bad or how intense the earthquake was. The other way to measure it is much more quantitative, so it uses a number, and that's what we refer to as the magnitude on the Richter scale. And in that case, you actually use the measurements from the seismograph and you put it onto the Richter scale, which gives you a number for how large the earthquake was. Earthquakes have very destructive effects, and can cause a lot of problems and damage and death. And you'll see more of that in the video that follows. And finally, here is our earthquake risk map. So you can see that for the most part, we in Wyoming are in the minor damage zone, but you can see how that changes throughout.